Today I will be talking to you about our pathways for power-to-liquid fuels and chemicals. Our institute, the Fraunhofer ISE in Freiburg, southwest Germany, is mainly focusing on solar power, photovoltaics and thermal power. But we also have the business area hydrogen technologies, where we're researching thermochemical processes, chemical energy storage and fuel cell systems. My team, Power to Liquids, is within the activities of the department Thermochemical Processes. And in this department, these are the delays I was told. We're developing processes for the power to liquids chain, converting renewable energy into liquid energy carriers. But we also investigate catalytic evaporation processes to burn liquid fuels in the gas phase and with less emissions. We are also turning biomass into catalysts for greener chemistry. And in everything we do, we are looking at the LCA, the life cycle assessment of what we do, so the technological, economical, and ecological evaluation. Why are we interested in power to liquids? For that, we need to look at the greenhouse gas emissions Germany has set for itself. I'm taking the example of Germany here because it's the most familiar to me. Here we see that in the electricity and the transport sector, we are significantly missing our targets right now. In the others, it's looking pretty well, but in electricity and transport, we need to get back on track. And to achieve this, we're looking at coupling these sectors in order to promote the synergies that are possible. While we have completed in this energy transition, we have completed the first phase, fundamental technologies, where we have seen a price digression and deployment of the first solar and wind farms. Now we need to think big, install huge power for electrolysis, and also start producing large amounts of power to liquid carriers, chemical energy carriers, in order to defossilize our energy system in the end. So this is why we're investigating the power to liquid process chain, where in the beginning we have a sustainable power generation, renewable energy, and some kind of CO2 source. This may be an industry process, steelworks or cement industry, biomass, and in the future we might also consider carbon sequestration from the air, but with the concentration of 400 ppm, this is still some technology cycles away. With the renewable power, we will then conduct an electrolysis. The greener our energy, of course, the greener our hydrogen. And with the hydrogen and the carbon dioxide, we can then perform all kinds of chemical syntheses. For example, to methanol, and from there on. Methanol is a very versatile chemical, platform chemical, produced at 100 million tons per year, I think. And it can be used in the mobility sector, for cars, for ships, to produce materials. In almost any polymers, you find methanol somewhere in the process chain, or to produce energy again. That was a bit abstract. Now let's look at a simulation we have done, a techno-economical assessment. We see for this case some variable parameters that are unusual for methanol synthesis, because in the beginning we have a fluctuating electricity input. We want to run our electrolyzers during for a lot of hours to keep to have a good return on our capex investment. But of course, that means that we will need a hydrogen storage, because it's not always possible to run the electrolyzer on high loads. The methanol synthesis is also not a very dynamic process until now. We like to run it for 8,000 hours straight during the year, and that is a big challenge. So we need a buffer, but a buffer is expensive, so we have to see how this goes into the costs of methanol. And in this paper we wrote for sustainable energy fuels, we have a methanol price of about 600 euros per ton, which is more than the price that you will pay today for fossil methanol. but we have a CO2 avoidance cost that will probably give us a bonus under the right legal framework. So here in the future we might get to a point where it's getting profitable. Everybody loves hydrogen. We want to use it everywhere, but storing it is hard and expensive. So if we want to couple this with the industry and do some grid balancing, we need to look at a project where we're converting CO2 waste into an asset. And this is the project Carbon to Chem we're working on together with industry partners. So here we're dealing with steel mill gases, very rich in carbon monoxide, carbon dioxide, some hydrogen and a lot of nitrogen as well. And right now the steel mill will burn its steel mill gases to produce heat and electricity. But in the future we want to turn the steel mill gases into fuels, plastics, fertilizers, and also use energy from renewable sources to power the plant and not have the plant power the grid. For this, Fraunhofer is contributing a methanol mini plant that is operated 24/7 with a recycle loop. It's looking like this. We are simulating, we're doing process development of the methanol synthesis in non-stationary conditions, which I mentioned earlier is not that easy for methanol. And we're doing life cycle assessments of all the steps we're doing. Our mini plant has 2 reactors which are being operated in an adiabatic way. We have a recycle loop. The plant is producing about 1 kilo of raw methanol per hour. Depending on how much CO2 you have in the feed gas, you have a little bit more water than with a traditional carbon monoxide rich synthesis. And this plant is now still being tested at our labs in Freiburg and will be moving to the Technikum, a newly built lab at the steel mill in Duisburg, and then will be operated with cleaned gases from the real process and hydrogen from an electrolysis on site. Good. Now we have methanol, but what else can we do with it? Upgrading methanol and address even more markets is then, of course, excuse me? Upgrading the methanol is super interesting, and looking at these oxymethylene dimethyl ethers, or shorter OME, we can tackle different markets. So these ethers are non-toxic. They burn pretty cleanly because they don't have any carbon-carbon bonds. Here we see how it compares to diesel, also in terms of GHS pictograms. They're very interesting blend-ins for diesel fuels because their properties are comparable, and they also have good solvent properties. They can absorb CO2. Today, the pathways to produce them are energy and cost intensive, but we're working very hard to get these cheaper and more efficient. One of our strongest assets here is that we have a simulation platform capable of delivering balances of plants, efficiencies, costs, as well as the ecological impacts. And we're also looking at the heat integration early on. Here, the flexibility of a MATLAB simulation combined with the industry standard of Umberto lifecycle assessments can give us an edge into very early simulations, while the TRL, the technology readiness level, is still pretty low. There's more liquids I'd like to talk to you about, but for today I will stop here and give you the take-home messages. So our electricity production needs to change, and we will need to store large amounts of electricity for example, in the form of liquid energy carriers. And these are fit to the task because they have a high energy density and they fit in well with the existing infrastructure. We think that methanol is the key component. It's a platform chemical, and it's used as a fuel and as a base for chemicals. Steel mill gases are a huge source of carbon oxides and hydrogen, and steel mills are probably going to be around for quite long, so we should definitely use their top gases. In the project Carbon to Chem, we're investigating how to transform these steel mill gases into fuels and chemicals. Oxymethylene ethers are made from methanol and are very interesting as diesel fuels. And at Fraunhofer ISE, we're looking at these processes, we're developing these processes, and we're always looking at the technology, the environmental impact, and at the costs as well. So with this, I'd like to acknowledge my team that's been working very hard with me, and at the funding from our Ministry of Research and Education, who have been supporting our work in the Carbon to Chem project. So I'd like to invite you to come at the booth C58 to discuss power-to-liquid pathways with me and my colleagues, and enjoy a good cup of coffee with us. My colleagues from the fuel cell department are going to be around tomorrow and Thursday for more presentations, and of course we would like to see you here in the audience. Thank you very much.
Thank you very much, Max Hadrich. Are there any questions from the audience? Okay. So I'm wondering, when is this, do you think it comes to the market, or you will go a step further? Do you have partners where you think about collaborating? Like right now it's on the research focus.
Yeah, so the project Carbon to Chem is supposed to run for at least 10 more years. And the phase 2 and 3 are looking more at the implementation in pretty large scales. Right now we're at a research and development stage, but the plan is to build pretty huge plants and convert a large portion of these steel mill gases into fuels and chemicals.
Thank you very much. So if you want to discuss the topic any further, it's booth C58. He will be around today at least.
Yeah, tomorrow as well.
Tomorrow as well, perfect. Yeah, thank you very much for the presentation.
Thank you.